Welcome back everyone. In this video we're going to be looking at more examples of cash flows that include uniform payments aka annuities, and we're going to be introducing gradient payments which will be denoted by G. So let's look at the case of uniform payments. Okay, and let's suppose I have a cash flow where I start off with a present amount of, let's say, $1,000. This could be equivalent to a loan that I take or some form of money that I borrow from somebody, and I need to pay this amount back in 3 years, and each year I'll be paying an equal installment amount A. Alright, so the idea behind solving this problem is that the value of these negative annuity payments must be balanced by this positive cash flow at year zero. Now, if we compare that to how a gradient payment looks like, I'll once again have a cash flow here. So at year zero, the amount withdrawn once again is equal to $1,000. And let's say at year one, nothing happens. There is no payment that I make, and there's no money that I receive from the other party. The next year, I pay a certain amount, let's call that G, to the lender. And the following year, I pay double the amount that I paid in year two. And as you can see the pattern here, each year the payment is increasing by a constant G. So for the if I take this to the nth year, the negative cash flow at the nth year is going to be n minus 1 times G. Alright, and now once again, the idea behind finding the value for this G is that all these negative cash flows must balance out this positive cash flow. So in order to get those values, we can start off by using analytical formulas. So the first formula is for when you have a uniform series of cash flows. So you start off at year zero by taking a loan where P is the present value of that loan, and each subsequent year you're making a payment of A. Okay, each subsequent year, and N is gonna be the year in which you make your final payment. So that's how the structure of the problem has to be laid out for you to apply this first formula. At year zero, you have to take the loan and you have to start paying it right off the bat at year one, year two, year three. There can't be any delay. If you don't pay anything at year one, then this formula is no longer going to be applicable. So make sure that your cash flows have the right format, have the right setup before you start plugging and chugging. Similarly, for the second formula required to calculate the gradient payments, you also need your cash flows to be set up in such a way that at year zero, you take the payment, and at year one, there is no payment. Keep that in mind. At year one, there is no payment. You make your first payment at year two, and then at year three, the amount is doubled, and then At year 4, it increases to 3G, etc., until it has been finally paid off in the nth year, and that amount is going to be n minus 1 times G. So this structure of your cash flow is quite necessary. Keep in mind that if you don't have this structure of your cash flow, you won't be able to use this and this formula that has been derived for you. So make sure that you have a present value, no payment at year 1, and each year subsequently the payment is growing by the constant amount. Now, in more practical cases, you'll encounter cash flows that are much more complicated, that would often include a combination of annuities and gradients. So in those scenarios, I resort to using Excel. So let's say we'll do both problems. Let's start off with the where we're given the present value of $1,000, let's say, and we want to compare the cases where we make annual payments in 3 years. Okay, and so 3 uniform payments, let's compare that with, oops, this color scheme is switching around, is making things a bit slow, my bad. So let's compare 3 uniform payments with 3 gradient payments, G, 2G, and 3G. Okay, so our present value is $1,000. Let me zoom in for you, and let's make sure our formats are in the currency version of the numerical formatting. And let's suppose we have the interest rate is 0.10, so 10% interest rate. This, all right, better. So all right, we can just like plug and chug the formulas that we have here, and really like that should not be a problem for you. This is here, Excel is just performing the function of a calculator, nothing more than that. So I star multiplied 1 plus I, and my period, since I'm making for the uniform payments, it's 3 years. All right, so I just have to be careful with my parentheses, as you always should be when you're using Excel or MATLAB. 1 plus I raised to power 3 minus 1. Okay, so $402 is the annuity amount that I'll be paying, and let's see what the gradient amount is gonna be. I'll be plugging in the formula like I did earlier. So this is gonna be P times I star times 1 plus I. Now N is the final year in which you clear your payment, so keep that in mind. In the case of the uniform series, oops, never mind. In case of the uniform series, we cleared out our payment in year 3, but in the case of gradient payments, we're clearing out our balance on year 4. So N has to be the final year of your payment in this formula. And that's a common mistake that most students are gonna make, and you have to be careful that N is the year when you're applying this formula, the final year at which your account has been cleared. You check off the balance. Okay. All right, everything looks good so far. Alright, and then I have to divide this by the denominator term, 1 plus I raised to power 4 minus the interest rate times 4 minus 1, and that should be it. Alright, so the first, at year 2, the payment is going to be $228. The next year it's going to be $456.82, and the next year it's going to be, oops, 3 times of your gradient payment. So this solution was demonstrated by using by just plugging and chugging the analytical formulas that you'll be presented in your textbook. Now, I personally really prefer to solve these problems by balancing out cash flows manually, because it gives me more control over how I manipulate my cash flows. So if you watch the last video, you'll understand you'll probably remember how I set up my list of cash flows. I set up a discount factor, and then I balance them out by taking their sum and setting it to 0. So let's just demonstrate it. Cash flow, actually I want 4 cells. Yeah, 4 should be enough for the uniform payment. All borders, and I don't need that. No border. Okay. Oops. Better. Alright, so we have year, the cash flow in that year, the discount factor, and the discounted cash flow in that year. Alright. So you're starting off from year 0 all the way to year 1, year 2. Alright, just drag it down. And at year 0 you have a positive. You're taking the loan of $1,000, and right now we don't know how much amount we'll be paying, so I'm just gonna leave a guess value here, make that an absolute reference. Let's say my initial guess was 100. Oh, and it has to be negative because I am paying it off. My interest rate was equal to 0.1. The discount factor for each year is going to be 1 plus the interest rate, absolute reference, and raised to power negative of that year. So as the time progresses from year 0 to year 3, the discount factor is going to decrease, hence the time value of money is going to decrease with time. So in order to get the discounted cash flows, that's just going to be the product of the cash flow and the discount factor. And once I drag this down, okay, we're running a little late on this video. We'll continue this in the next part of this video, and in which I'll show you how to get the NPW and set that to 0 by using either GoalSeek or Solver. So alright, see you guys in the next part.